specific functional group. If not anything else, they would definitely have a molecular weight or a molecular mass. And we make use of one or more of these physical properties to separate and to identify them. Yeah, because you do an analysis to look at one particular compound out of your mixtures or to look at everything that is present in a mixture. So you need to separate them, and we make use of their own physicochemical properties to identify and separate them. So what's a mass spec? Mass spec as a technique, as an instrument, that's what it is. It's a weighing machine. Okay, you stand on it and it tells you the mass. Today most of the people are scared to stand on it. At least I am scared to stand on it because it tells me I'm 20 kgs overweight. Okay, so that's what exactly a mass spec does. You put in your sample, it tells you the mass of your compound. Okay, so whatever mass spec you're using, whichever company you're using, the basic layout remains the same. You have a sample, there's a sample introduction system, it goes to the ionization region. And ionization is the first thing that you do to your sample, because if you're not able to produce ions from your sample, you basically go nowhere on the mass spec. Whenever I go for lectures in institutes and research labs, people often ask me a question: what do you think is the limitation of a mass spec? I said, no. A mass spec has no limitations. The limitation lies in the capacity of ionization. If your sample cannot produce ions, if it does not have the capacity to get ionized, there's nothing that a mass spec can do. And if you can produce ions out of your sample, you can analyze basically anything on this earth using a mass spec. Okay, so why people are using LC-MS these days? Why should even one think about it? When I did my PhD about 20 years back, I never even saw a mass spec. I finished it on a Shimadzu spectrophotometer. But then why suddenly all these mass specs have come up? Why it has become such an important thing? These are some of the reasons I listed down why somebody would even think of using a mass spec for their analytical needs. Out of these, number 2 is something which has become very, very important: structural conformations and structural identifications. And this is also one of the prime requisites of a pharmaceutical analysis, a pharma analytical domain. These are the different mass specs that you see across the globe. You have a QTOF, you have an ion trap, then you have a TOF. And if you see on the other side, you see triple quadrupoles and a single quadrupole. But what is important on this slide is this arrow down below. To quantitative applications, you see that there is a subtle shift in the technologies. From qualitative to quantitative, you see the shift from full scan instruments like TOFs and QTOFs to quadrupole-based instruments. So the purpose, what the message that this slide gives is, if you have a mass spec, you don't become God. You basically cannot do everything. Whatever the application is, I classify it under only 2 heads: qualitative or quantitative. Okay, so whatever a lab does, whatever an analytical research lab is doing or analytical lab is doing, they basically either come under qualitative analysis or quantitative analysis. So as you move from qualitative to quantitative, you see that there is a difference of technologies that come into picture. A quick slide on ionization sources. I said, unless you are able to produce ions from your sample, you go nowhere on the mass spec. So these are some of the techniques, some of the ionization sources that are used to produce ions from your sample. And these are the analytical domains that are covered by different technologies. The 2 or 3 most commonly used technologies to produce ions from your sample is ESI, which stands for electrospray ionization. Then you have APCI, which stands for atmospheric pressure chemical ionization, and then atmospheric pressure photoionization. And if you see the diagram, what it gives you is a relationship between molecular weight and ion polarity. So more polar ions, heavier ions, you basically use ESI, and then APCI and APPI. So this is a general thumb rule. Looking at the compound, looking at the structure of the compound, you can predict whether it's polar or non-polar, and you can try out an ionization technique to produce ions. So that was a little bit of basic on the mass spec. And coming to applications, if I refer to pharma, I see there are three basic applications, three major applications, which is bioanalysis, drug discovery screening, and impurity profiling. Impurity profiling also refers or relates very well to the theme of the seminar, stability studies, because if a drug undergoes decay, if the drug undergoes degradation, it produces impurities. It also produces metabolites if it is undergoing degradation through a biological system. So these are the three major applications that a pharma company or a pharma industry would look at in terms of mass spectrometry. But if you see the three things down below, bioanalysis is basically 90% quantitative. I know what I'm looking at. I just want to find out what is the concentration of the drug that I'm studying in human serum. Sorry. And if you see drug discovery, it's about 90% qual, that's qualitative. And impurity profiling, whatever anybody says, it is basically 90 to 100% qualitative applications. You're looking at the kind of impurities that are being produced or that are being generated from a batch or from a degradation study. So, giving a quick picture of what a triple quad looks like. That's a triple quad, QQQ. Basically a quantitative instrument. It does nothing else but quantitations on a very, very dirty matrix. So bioanalytical applications are very well done on a triple quad instrument. That's one of the mass analyzers. How it works is you have the first quadrupole, which filters out a single ion from a mixture of ions. In this case, it has filtered out 210. 210 is the molecular mass of the ion that is being analyzed. And the collision cell is basically a fragmentation device. You break this 210 into different fragments. So when you break something, you get a lot of information about the structure of the compound or structure of the molecule. The analogy that I like to give is, you know those make and know blocks which the kids play with. Okay, so you give them a house made of the blocks. So they would take it apart and then try to reassemble it. And this is exactly what it happens. You have a compound which has a certain structure. You break it and then you try to analyze or decipher what could be the structure of the compound. And the third quadrupole looks at one or more ions for quantitation. So these are some of the results, screenshots that a triple quad would give you. The top one is the MRM chromodiagrams, that's multiple reaction, basically used for quantitation. You have a drug which you have injected into the blood. It undergoes a certain degradation or metabolism and produces metabolites. And then you can quantitate the level of the parent drug as well as individual metabolites at different stages of excretion. And what you see down here is a linearity curve. So you have a very, very high dynamic range over which you can quantitate your compounds. Another mass spec, which is also known as single quad, it basically gives a second dimension to your analysis. The top trace that you see is a UV trace. So you have 4 compounds and a very small 5th compound as well at the bottom after a UV4. But when this goes to the mass spec, what mass spec shows you that you actually have 5 compounds in there. So I'm going to spend 2 minutes on this. You have HPLC as an analytical tool. You have a peak that is coming out of the HPLC. You're not sure whether the peak is a pure peak or no. Okay. So when you're doing method development, you would try and see if that peak splits into 2. Okay. So you would do all kinds of analysis on that. You would vary the runtime, you would vary the flow rate, you would also vary the pH, etc., to see if that peak splits into 2. Okay, but the end of the stack, what it will tell you is the peak that came out of the HPLC and